All right, well, hey, welcome to day 2 of differential equations. Last time we just kind of set the table with what differential equations are and how they behave and how to recognize what kind they are and that sort of thing. And talked a little bit about slope fields so you can get a visual representation of what happens with solutions and all that good stuff. And today we're actually going to start solving them. We're going to start learning techniques for solving differential equations. And we'll start with first order. And in fact, we're going to start with first order linear, the ones that are linear functions. But before I do that, I do want to open it up to any questions about the homeworks. Anybody get in there, have any issues with anything so far? All right. This is rare, but I will take it. Sounds like we don't have any issues yet. It's either because, well, one of two things. Either you haven't started it yet, which knowing this squad is like most of you, or hopefully for those that did start it, you're seeing that this first set isn't that difficult because it's really just, hey, checking and see, do these functions actually satisfy the differential equation? Find the C from the initial values, things like that are pretty straightforward. All right, cool. Well, I'm glad to hear that. So then I guess what we're going to do is go ahead and dive into how do we solve these guys. All right, so give me 1 second and I'm going to hop up to the whiteboard. All right, so today, let's actually get to the how do we solve these things. So you may remember that when we talked about classifying all the different types of differential equations, one of the things that we broke it down into, we started with just ordinary versus partial. And again, this class, everything's going to be ordinary differential equations. But then within the ordinary, we talked about the order, right? What kind of order our differential equations are. So we're going to look at solving first order. Okay. So we're going to look at solving linear first order differential equations. So this is kind of a, well, not kind of, this is a very small chunk of differential equations, right? Already we went down the ordinary path. Within this ordinary, we went to first order, meaning just a first derivative. But then we even split down further and we went to those that are linear. Now, linear, again, all that means is that the y-ness, so the y's, the y primes, that the equation is linear in terms of those. With your other variable, we're talking x or t. I mean, you can have x squareds, you can have sine of t, you can have all that stuff and still be linear, as long as your y's and your y primes are not being multiplied to each other, are not being squared, or not being, all the other things that make things nonlinear. All right, so if we're talking linear first order, all linear first order can be written in this form, where you have y prime plus some function of x times y equals some other function of x. So any differential equation that can be written in this form is linear first order. So hopefully you see the first orderness. That just jumps right out at you, right? There's the y prime. But it is linear because notice that there's nothing attached to the y prime. This y, the only thing attached to it is the other variable. Okay, so that doesn't affect linearity or anything like that. Linearity. So this thing is linear first order. All right, now some more terminology. This is going to matter. If g of x equals 0, if this guy is 0, it's called homogeneous. So I'm sure you've heard that term somewhere else along the line because it's a term that we use a lot. But in the context of differential equations, it's a homogeneous differential equation if it equals 0. All right, so if g of x is equal to 0, then this is a homogeneous differential equation. If g of x does not equal 0, it's non-homogeneous. Right? Okay, so if you ever hear me say homogeneous, it just means equals 0. All right. Now, in order to solve linear first order, we're actually going to start with ones that are homogeneous, because those are easier. I mean, you guys know this. When you have things that are equal 0, or you're plugging in 0, tend to be a lot easier. No different here. All right. So let's start with this homogeneous case. And once we get comfortable with the process for solving the homogeneous, then we'll move to the non-homogeneous. All right, so that means if we're looking at the homogeneous, we've got y prime plus p of x times y equals 0. So this is what a linear first order homogeneous differential equation looks like. Do we have any more descriptors on that? Linear first order homogeneous. But it's all about classification. If you get anything else out of this class, out of differential equation, I hope that you get that it's all about recognizing forms. Because once you know the form, you're going to know what to do. We have a recipe, we have a technique for every form. All right, so here's homogeneous. Now, it turns out that the homogeneous always has the same kind of solution. There is a function that will satisfy any homogeneous differential equation, regardless what this p of x is. Does anybody see it? Anybody see a solution that will always work no matter what p of x is? So Victor, is it wrong that this reminds you of linear algebra? No. They are intertwined. And in fact, some places teach them both together. Like you'll have a class that's linear algebra / differential equations. But anyway, so no, it's not weird that you're thinking that way. And also, thank you for giving me your solution that you think, and I see that Bijan put that in there as well. Y equals 0. Yeah, it turns out that y equals 0 is a solution. And it always will be. Because think about it, you differentiate 0. Well, if y is 0, it's constant, its derivative is 0. So we get 0 plus something times 0, of course, that equals 0. And you're right, Victor, this is the one that we call a trivial solution. So y equals 0 is a solution, but it's trivial.
So is this p of x a constant or a function?
It's a function, but it's a function of x. So there are no y's in it, but I mean, it could be x squared, it could be sine of x, it could be e to the x, it could be insert your favorite function. It also could be a constant, right? We could write y prime plus 3y equals 0, and that's fine too, but it doesn't have to be a constant. So it's just any old generic function of x. But again, that doesn't really matter if y is equal to 0, right? Whatever this is, if I multiply it by 0, I'm still going to get 0. So in terms of the trivial solution, we don't care about p. We don't care what that looks like. So here's the deal. If I ask you for solutions to homogeneous, yes, I know y equals 0 is a solution. I don't care about that solution because we already know that that's a solution. Right? That's the answer that would get the eraser flung at you in class. Right? Like, yeah, shut the hell up. Of course I know y equals 0. But that's a trivial solution. So we are guaranteed a solution no matter what. But the question is, are there others? Are there others? And if there are, how are they determined by what this p of x is? Like what happens when it's x squared? What happens when it's negative hyperbolic cosecant of, whatever? Like what happens when it's those other things? So let's investigate that. Let's actually look at what happens non-trivial. All right, well, the way we're going to do this is to separate the variables. So this is something you should have seen through our sequence. It would have been quarter 2, back when you guys had Larry last year. For those of you who didn't take it at our school, it would have been somewhere in the middle of calculus, after you learn integrals. But this is separation of variables. So let's just do this generically. The y prime plus p of x y. I'm going to write that as dy dx plus p of x y equals 0. And I'm just going to do a little bit of algebra. I'll move that p of x dy, or sorry, p of x times y to the other side. Make that a minus. And then I'm going to move things around a little bit. So I get dy over y is equal to negative p of x dx. So there was just a little bit of algebra. And I separated it. So I've got my y's on one side and my x's on the other. So does anybody remember why this is useful? Like why we do this?
Is it so we can integrate?
Yeah, because now we can integrate. We have just y's on the one side and just x's on the other. So let's integrate this thing. All right, so the 1 over y dy, the integral of that is the natural log. So we're going to get natural log of y equals the integral of minus p of x dx. Obviously, I can't integrate that thing because I don't know what it is. So you tell me, right? You tell me what that is, I can do the integral. But if we're going to do it generically, we just have to leave it like that. But notice that there's only one more step here to get y. Y, if I want to free it from that natural log, I just have to use exponentials. And so I get y is equal to e to the integral of negative p of x dx. And check it out. We just solved every single homogeneous linear first order differential equation. Yay. Yeah, yay. I mean, it's not exactly trivial, but it ain't hard. Because we've got a form for it. We're just going to do the same thing every time. Whatever this function is being multiplied to y, you're going to multiply by -1 and then integrate it. And you're going to put that as your exponent on e, and there's your answer. Okay, I don't know if you quite see the power in this yet, so let's do some. Let's actually we'll do 3 of them here real quick. This will be crazy fast because we've already done all the work. We did all the work right there. Now it's just a matter of putting in the respective pieces for whatever our function happens to be. All right, so let's look at this one. Let's go with y prime plus 2xy equals 0. So first order, linear, homogeneous. And in the context of our generic thing here, p of x is equal to 2x. All right, so here's our solution. Y is going to equal e to the negative integral of 2x dx. I just pulled the minus sign out front of the integral. Right, no big deal. Okay, so well, the integral of 2x is x squared. So we get y equals e to the minus x squared plus c. Can't forget to put in our plus c. But hopefully you guys all remember the trick that the c that's being added there can come out as a different c out front. And there you go. here is the solution to that differential equation. The general solution, right? If we wanted a particular solution, we'd have to have an initial condition. But the general solution is there. It's done. And I know many of you, because you know calculus and you know me, you're waiting for the yeah, but. Nope. There is no yeah, but here. This is it. You're done. I mean, you can check it. It's super easy to check, right? Let's just confirm it. This is the other nice thing about differential equations. When you solve them, you can always tell if you're right or not. You can always see if it's a solution just by doing a real quick check. So let's see what y prime looks like. Well, the c is a constant multiple. E to the minus x squared, you're going to get e to the minus x squared. The chain rule, you're going to get a minus 2x. We get minus 2xc, e to the minus x squared. All right, well, if you plug that into the differential equation, so we get minus 2xc e to the minus x squared plus 2x times ce to the minus x squared. And it certainly doesn't take long to see that that equals 0. All right, there you go. That's literally it. All you have to do to solve these. All right, so here's another one. Just to prove to you that it really is truly this quickly, or this quick. We just got to figure out what the P is, right? Plug it in. So here's another one. Let's go with xy prime plus 4y equals 0. So again, hopefully you can look at that and see that it's linear, first order, homogeneous. All right, first order, homogeneous, linear. All right, so in order to solve it, we just got to figure out what the P of x is. So what's P of x here?
Four.
Yeah, sure, go ahead.
All right, we good with that? P of x is 4? It's right there, right? Oh, Bradley, I got you. It's not actually 4. What's different about this one that we didn't have before?
The P of X is on the Y prime.
Okay, so there's something on the y prime, and we can't have anything on that y prime. We need it just to be y prime. So what we have to do first is divide everything by x. So that this turns into y prime plus 4 over x times y equals 0. So I guess if, when I said there is no yeah, but maybe this is it. The only thing that you do have to watch out for is that it's in the right form. And to jump to this solution that we've got boxed, we need it to be y prime all by itself. But that's easy enough to take care of. Like whatever's in front of that y prime, just divide everything by it. And then you're going to be in the form that you need. All right, so yeah. I bring these things up not to try to trick you, but because it's going to happen when you see like differential equations are not always written in the form we want. Sometimes we've got to do algebra to get it there. So in this case, P of x is actually 4 over x. All right, but now that we're there, let's get our answer. So y is going to equal e to the negative integral of 4 over x. 4 over x, that's 4 natural logs of x plus c. I can bring that c out front. So we have y equals c times e to the minus 4 natural log of x. But I'm also going to do one more thing now. I'm going to simplify this using the rules of logs. That minus 4 can come in as an exponent. So we have natural log of x to the minus 4, which means that e is going to cancel with that natural log. And what I'm left with is y equals c times x to the minus 4, or y equals c over x to the 4. So there's the solution to this differential equation. It's c over x to the 4. But again, fast and easy. What was tricky about this one, other than making sure we were in the right form at the start, is the rule of logs stuff to simplify. If you're a little rusty with that, go back and look at them, because we're going to do that kind of simplification all the time. Anytime you get a natural log from the integral, you're going to do something like this, because since we've got e raised to that power, we want to take advantage of the fact that e and natural log cancel each other out. All right, well, there you go. There's the solution to this differential equation. All right, well, let's make it tricky. He says, not really meaning it. Because here's what I'm going to do. We're going to do one more, but this time I'm going to be cruel. And I'm going to make it an initial value problem. So let's say we got y prime plus 1 plus sine of t times y equals 0. But I'm going to tell you that y of pi over 2 is equal to 1. All right, so really the only thing I did here, I didn't change what we're going to do. We just added one more step. There's going to be one more step at the end where we plug in and we actually find C. All right, so let's do this. Let's start by getting the P. So now you remember the trick. You go, okay, first thing we should look at, do we have y prime all by itself? Yes, y prime is all by itself. So we don't have to do any kind of algebra. So it is what we think it is. P of t is 1 plus sine of t. And the fact that it's t and not x. All right, so then our solution would be y equals e to the negative integral of 1 plus sine of t. So we're going to get c times e to the negative t plus cosine of t. The integral of 1 is t, we get negative t. The integral of sine is negative cosine, so negative negative becomes a plus. And the plus c, I just went ahead and put it out front, because it always goes out front. All right, so there's our general solution. So now let's get the particular solution by plugging in our point. Okay, so we know that when we plug in pi over 2, we get 1. So we're going to get 1 equals c e to the minus pi over 2 plus cosine of pi over 2. The cosine of pi over 2 is 0, so that's gone. So we get 1 equals c e to the minus pi over 2, which if we solve it for c, gives us e to the pi over 2. So that's the constant for this one. So now we just plug that in for C. Then we get y equals e to the pi over 2 minus t plus cosine of t. And I went ahead and just combined those using the rules of exponents, right? If I take e to the pi over 2 times this stuff, it just means I'm adding the pi over 2 in the exponent. All right, but there it is. There is the function that solves this initial value problem. All right, so we just did 3 examples of the homogeneous after solving every single one, right? We found the pattern. So how are we feeling about this at this point?
Pretty good.
I'll take pretty good, right? Because I can't see your faces or anything. I can't tell if you're like bored. But notice it's just like, every single one of these, we did exactly the same thing. Once we were in the right form, we just took that p, we integrate it, slap a minus sign, put an e to that power. Done. Okay, so really procedural. So as most of you know, I like to talk about monkey math, right? Math that you can train a monkey because it's just procedural. This is total monkey math. There's a recipe. Just follow the recipe, right? So learn that recipe, practice it a few times. You'll get bored. Probably by the time you do the homework on this, you'll be bored to death of doing the homogeneous, because it's the same thing every time. All right, so that's homogeneous. Cool. So what happens if it's non-homogeneous? All right, well, first things first. When it's non-homogeneous, we're not actually guaranteed to have a solution in. But the homogeneous, we knew for sure we were going to get y equals 0. But that's not the case anymore when we go to non-homogeneous. All right, so non-homogeneous just now means that it actually does equal something else. All right, so I just put G there because I think that's how I learned it. But looking back at my notes real quick, I want to match what the book does. The book calls it F. Okay, so we'll go like that. All right, so here's the deal. 0 isn't going to be a solution anymore. Not necessarily, right? Because if y is equal to 0, we already saw that all of this stuff equals 0, which is not going to make this true if f of x is anything but 0, right? If this equals x squared, if this equals negative cosine of x, if it equals whatever, now 0 isn't necessarily a solution. Okay. Well, we're not guaranteed a solution, but let's see if we can find a solution. See if we can find a solution if it exists. All right. You're going to love this. And when I say you're going to love this, you're not going to love this because it's going to feel completely wrong. I love this. Again, you guys know how I think, so you're going to understand why I like this. All right, so we're looking for an answer, right? I have no idea what that answer is. No clue whatsoever. If it was homogeneous, I could figure out an answer, right? I mean, we just did it. So there's a process to do it. So here's what I'm going to do. let's just say that we find a solution to the homogeneous. And I'm going to call it y sub 1. Because I can find that. We know we can find that. And I'm even going to say, even though there aren't really any of you that are in here that are like this, but you know the kind of students that I'm talking about. A non-trivial solution. Okay, let's go with something that's non-trivial. All right, so let's let y1 be a non-trivial solution to the homogeneous. So really what that means, we know then that y1 prime, that plus p of x times y1 is going to equal 0. Right, that's what that means. So I'm just putting that there so that we remember what it means. All right, so here's what I'm going to do. I'm going to guess a form for the solution to the non-homogeneous. And what I'm going to do is I'm going to say that a solution to this non-homogeneous is going to be some function of x times y1. All right, let's just pause for a second. So here's what I'm doing, right? I'm finding a solution to the homogeneous, and then I'm just saying, all right, I know that whatever my solution is to this thing can be written as a multiple of y1. I can always do that, right? Let's say that y1 was e to the x, and I want a solution of x. Okay, well then u would be x over e to the x, or whatever, right? So I can always turn it into the function I want by multiplying by something. So really what this comes down to then is I have to figure out what is that something. So that's going to be our goal. Our goal is going to be to see, can we find u? All right, so Victor, hold on, you just said something about a basis. I got to read this closely. So, so like y1 is a basis for solutions. Why, yes, it is. Except we're going to go a little bit beyond that because it's not exactly a basis because u doesn't have to be a constant. It doesn't necessarily have to be a constant. And when you talk about bases in linear algebra, it was you're doing linear combinations of them. But it's the same kind of idea. It's exactly the same kind of idea that we can write out all solutions as some multiple of the solution to the homogeneous. Just that multiple may not be constant. Man, you totally are in linear mode, Victor. I'm impressed. And slightly scared for you, actually. Slippery slope. Next thing you know, you're going to be like me and Larry. Scary. All right, so here's our goal. We're going to see if we can figure out what u is. All right, now, to help us do that, to help us figure out what u is, let's take this guy and put it back into the differential equation. Let's actually see what happens if we have y equaling u times y1. What happens when we put it into this differential equation? Okay, well, if y is equal to u times y1, then y prime, we have to use the product rule. So it's going to be u prime times y1 plus u times y1 prime. All right, so this is practical. I'm dropping the of x's because. All right, so let's put it into the diffie-q and see what happens. So we go back to that original non-homogeneous, the one that's up here in purple, and let's put these things in. So we're going to get u prime times y1 plus u times y1 prime plus p of x times y. Well, y was the u times y1. And that's going to equal f of x. So I'm going to group these a little bit. You'll see why I do it this way in just a second. I'm going to keep that u prime y1 out front, but then I'm going to factor out a u from these other pieces. So I get y1 prime plus p of x times y1. All right, so far so good. Just plugging it in and we're seeing what happens. Let me draw your attention to something. Look at this piece that's in the brackets. Notice that that all just involves y1. And we know something about y1, right? Y1 was a solution, a non-trivial solution to the homogeneous. Does anybody see what's happening here? Have I connected, put the dots close enough? What happens to all the stuff that's in the brackets? Yeah, it's 0. Remember when I wrote that over there as a, hey, remember that's what this means? Yeah, perfect. Let's check it out. This stuff that's in the parentheses, that's exactly what's in the brackets here. This just equals 0. All right, so if all of that equals 0, this equation now becomes u prime times y1 equals f of x. And remember what the goal was. I wanted to figure out what u is. Well, if I divide by y1, I have here that u prime is equal to f of x over y1. So if I want to get u, all I got to do is integrate. So this magical, mysterious u of x, it's going to equal the integral of f of x over y1. Let me put a box around that. This doesn't finish the problem. This doesn't give us our answer because there's still another step, but it gives us the key. Because our answer is going to be whatever this is times the solution to my homogeneous. Right? So if you want to know what y is, your solution is going to be y1 times the integral of f of x over y1. And you can definitely put a box around that because that is our answer. Ta-da! There you go. We just solved every single linear first order differential equation. I know. It doesn't seem like we really did anything but just move stuff around and all that. But there is the process. That's the process now to solve any non-homogeneous. And we'll do, we'll definitely do a few here so you can see the process. But look at what it's going to entail. First and foremost, we have to find y1. And y1 was a solution to the homogeneous. So even when you solve non-homogeneous, you're still solving the homogeneous. All right, so we're always going to end up solving the equal 0. So that whole little bit of the e to the minus integral of p of x dx, you're going to do that every time, no matter what. If it's non-homogeneous, then we have to put that into this to find the actual solution. I do want to warn you, because looking at this equation, I bet some of you really, 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 really want to just cross off those y1, right? But you have to remember that y1 is a function. It's not a constant. This is where it probably would be good for me to bring back the fact that these are of x. Because you can't bring non-constants in and out of integrals. It's not allowed. So the way you need to think about this is you do this integral first, right? You find your solution to the homogeneous, y1. You divide it into f. You integrate that. Then multiply by the y1. All right, so that's the process. This is how we're going to do it. There is a name for what we're doing for this process, because this process of taking a solution to the homogeneous and multiplying by something else, or taking a solution and multiplying by something else, trying to find that, that's common. We will do that lots of times throughout this quarter. It's what you do in a pinch, actually. If you run into a differential equation, and you're like, hey, I got a solution, but I need another one. You just do this. You go, okay, well, let's take a multiple of the one that we know, and let's see what happens. And so this method, it's called the method of integrating factors. So if you ever run across that name, that phrase, method of integrating factors, basically what it is you multiply a solution, a known solution, by an unknown function. In our case, that unknown was the u. All right, and then find the unknown. And so we'll even call this guy u. This is the integrating factor. Okay, so when you run into that, like if someone says, find the integrating factor, you're saying find u. Find this thing that we're multiplying. And use the name to help you. Right? Remember, factors, those are things that are multiplied together. And this is an integrating factor because it's the thing that we multiply by, and then we find it by integrating. Okay, so integrating factors. All right, so keep these things in the boxes in mind, I guess, in addition to the how we find y1. But this is how we're going to actually solve non-homogeneous differential equations. All right, so before we do an example, any questions at this point? Or are you even at a point where you even can formulate a question?
To find our non-trivial homogeneous solution, do we just assume that it's equal to 0, do it, and that's it?
Yeah, so that's the, to get the y1, y1 is going to be the e to the negative integral of p over x. The same thing that we were doing before. So yeah, you're going to just like pretend that it's equal to 0. Do it. And that's going to give you your y1. The one difference is, remember how when we did it, we always had the c in there? You don't have to have a c anymore, because all you need is a solution to the homogeneous. It can be any of them. So I always pick the one that makes it so that my function's easiest. So c is usually 1 or 0 or whatever, depending upon how c plays out. But yeah, so we're going to start by finding that, like we did. We're going to solve the homogeneous. Then we're going to use that to find u. And then we're going to put those two things together to get the solution to our non-homogeneous. All right, any other questions? Maybe let's just do one. Let's see how this works when we go through the steps. Because I think that will help. When it's general like this, just arbitrary, weird, random functions, it's sometimes hard to see. So let's just dive in. Let's do one here. All right, so you may remember the first example that I did for a homogeneous. I'm going to take that same differential equation, but just change it ever so slightly. I'm going to make it y prime plus 2xy, but instead of equaling 0, let's make it equal 4x. Okay, so we're just going to go through all the steps. So let's start by finding y1. So we pretend that this is homogeneous, so forget about what's on the other side of the equal sign. Just look over here, and we're going to do e to the negative integral of p. So the p of x is 2x, so we do the negative integral of that. So we get e to the minus x squared. So again, if this looks familiar, it should, because when we solved the homogeneous, that's the first example I did, it was y equals c times that. But again, notice how I'm not plugging in a c, because I don't need to. I can just have, I just need a solution to this. Or I guess I am plugging in a c. The plus c up here, it's a plus 0. If I brought the c out front, it's a times 1. Okay, so there's a solution to the homogeneous. But now we're going to use that to find our integrating factor. So we're going to get our u then. It's going to be the integral of f of x, so 4x, divided by y1. So I literally am just using what's in the second box over here, and I'm putting in the respective pieces. F, that's what we're equal to, the part that's making it non-homogeneous. So that was the 4x, and then I'm dividing by the solution to the homogeneous. All right, so this is the integral of 4x e to the x squared. We'll just bring that up as a positive. So we need to do this integral. This is one that you can do with u sub. If you let u equal x squared, then du is 2x, and so that pretty much gives you this. But the integral of this thing is going to be 2 e to the x squared plus c. All right, so that's step 2, basically. Step 1, solution to the homogeneous. Step 2, find your integrating factor. Step 3, profit. Oh wait, no, sorry, that's under parentheses. Step 3, multiply this factor times our y1. All right, so here we go. Here's our solution. Then y is going to equal the y1 e to the minus x squared times our integrating factor. So I'll go ahead and distribute. The e to the minus x squared times 2e to the x squared gives me 2. And then I just want to make it so that it's a positive and drop it to the denominator. No. No. Don't want to confuse you. Because that's perfectly fine. All right, so this right here, my friends, is the solution to this differential equation. Yay. Yeah, yay. There it is. So notice that it's really procedural. And just like the ones that were homogeneous, after you do a handful of these, you'll be like, oh my God, this is so boring because I do the same thing every time. Yeah, same thing every time. Find a solution to the homogeneous. Divide that into your f of x and integrate. Take that integrating factor, multiply by the homogeneous solution, and there you go. I do want to point out one more thing though. Notice that I did include my plus c in my integrating factor, right? I didn't just drop that one off. Unlike up here where I didn't have a plus c, but that's because when I found a solution to the homogeneous, it just had to be any solution. I could have chosen any of them. So I chose a nice one. I picked my own C. When we find the integrating factor, we're not finding a solution, we're finding all the solutions, which means that's where our plus C is going to come in. And we do need to have some sort of a C in our solution unless we have an initial value problem, because there's going to be more than one possible answer. There's going to be a whole class of them. All right, well, if you don't believe me that this is a solution to the differential equation, and that's totally cool if you don't, test it. Take its derivative, plug the derivative and this function back up into here, and what you're going to see is that it ends up equaling 4x. And so we do get true. All right, well, there's the process. So let's try another one. And this one, let's make it an initial value problem. All right, let's actually go ahead and find the C once we get there. All right, so I'm going to move back over to this side, which means I'm going to erase our little bits, but hopefully you got those down so you can reference them to think about what are the pieces that we have to do, and what are the things you have to do to find those, or what are the steps to get to our solution. All right, so let's go with this guy. We're going to go with x times y prime plus 4y equals 6x squared. All right, so here we go. Step number one. What do we do first?
Divide the whole thing by x.
Okay, good. Divide the whole thing by x. Bradley's like, oh, you're not going to fool me twice. Right? Okay, so we're going to divide everything by x. So we get y prime plus 4 over x times y equals 6x. Okay, good. Step number one is always going to be put it into the right form. But now that we're in the right form, what do we do? What's the next step?
And the homogeneous solution.
Okay, let's get a solution to the homogeneous. So we're going to do the old y1 equals. So y1 is going to equal e to the minus integral of 4 over x. All right, now this is actually the one that we already did. This was another one that we actually already did. So once you do the integrate, get the log, and use the rules of logs and all that good stuff, this ends up being 1 over x to the 4th. All right, so there's our y1. Okay, now what?
We'll find u.
All right, let's find u. So we're going to get u equals the integral of, so we need to take f of x and put that on top, so 6x. And then we need to divide by y1. We're going to divide by 1 over x to the 4th. All right, so that's the integral of 6x to the 5th. All right, if you just flip that over and multiply, that's the integral of 6x to the 5th, which is x to the 6th plus c. So there's our integrating factor. All right, so then to get y, we're going to multiply this by our y1. So y is going to equal 1 over x to the 4th times x to the 6th plus c. So we get x squared plus c over x to the 4th. So there's the general solution to that differential equation. And you know, because we haven't done one of these for a while, let's make it an initial value problem. Let's say that we also knew that y of 1 was equal to 3. Let's use that to find our c. So we're going to get 3 is equal to 1 squared plus c over 1 to the 4th, which tells us that c is equal to 2. So if we had added on that initial value, we find that our solution is y equals x squared plus 2 over x to the 4th. Okay, so 2 different problems. One of them was even an initial value problem. But notice that the process was exactly the same. I even color coded it for you. The teal was finding a solution to the homogeneous. The red was finding our integrating factor. The purple was putting those together to get our particular solution, or sorry, our general solution. So very procedural. very recipe. So if you're one of the people that loves the math recipe, if you love the, yeah, just give me the process and I do it, this is going to be your cup of tea. If you don't like that, you're not going to be a huge fan of this. I'll just tell you, me personally, I find this really boring. I love the trick. This whole, oh, let's find integrating factor. Let's just pull this out of nowhere. And I love that trick. But once that trick happens, and then you go, all right, well, now here's the process, I get bored. I just do the same thing every time. But that's me, right? That's why I'm not an applied mathematician. It's boring to me. Other people find it exciting, and that's the path to go down. All right, so how are we feeling about the non-homogeneous? What are your thoughts about this process at this point?
Pretty good.
All right, I get another pretty good. I think that was your answer to the last one too. So
Yeah, I don't know what else to say. I mean,
We're
it is
right
what
in
it is.
or maybe Bradley's not actually on. He just has some pre-built recorded statements, right? So his computer catches that I ask a question and then it just like, pretty good. Yes.
I'm not that clever.
You know, I had a Ferris Bueller's Day Off kind of moment. If you've ever seen that movie, right? He pretends to be sick, and so when the doorbell rings, it triggers a little his little cassette player for those 80s to play a little like stock thing. So, anyway. All right, so Bradley's feeling pretty good. How about the rest of you? Thumbs up? Yeah. Okay, cool. I'm seeing lots of thumbs up. That's what I like to see. Okay, so we're feeling pretty good. We see it's just a process. Well, check it out. You guys now know how to solve every linear first order differential equation. Whoa, we took care of that entire set. But that's a pretty small set, right? And we're not actually guaranteed that we always have solutions when they're non-homogeneous. So we still have to worry about that as well. But before we go there, I do want to give you an example of one that's a little bit more complicated. It's going to be complicated, not because it's a new process. It's going to be exactly the same process. But you're going to see why it's slightly more difficult. All right, so let me give you a differential equation here that we're going to solve. And it is going to be an initial value problem. We'll go ahead and do that extra step because we might as well. Right? There's just one more thing we have to worry about. But here we go. Let's say our differential equation is y prime minus y equals g of t. But what I'm going to tell you about g of t, well, actually, let me give you the initial value while I'm at it. We're going to have that y of 0 is equal to 0. So we know that our function goes through the origin. But here's the deal with g. G is going to be piecewise. It's going to be piecewise defined. So it's going to equal 1 when we're between 0 and 1. And then it's going to turn into -2 once we get beyond 1. All right, so I know you guys all know about piecewise defined functions. So I know that that's not really going to be an issue here. But the issue definitely is going to be, what about the iterating factor? because we actually have two different equations that we're solving, dependent upon where we are, right? The first one is y prime minus y equals 1. And the other one's going to be y prime minus y equals -2. So it's two different functions. But here's the good news. The good news is the process is identical for both of them. So we can actually kind of take care of both of them at the same time. So think about the first step. First step, obviously, we got to make sure we're in the right form, but we are. We got our y prime minus y, right? So it's y prime all by itself. So let's get the solution to the homogeneous. And the homogeneous doesn't care that this is piecewise, right? The homogeneous is just, this is big fat 0. So we can just solve the y prime minus y equals 0. Okay, so let's go to our y1. And that's going to be e to the negative integral of -1 dt. Right? It's always negative integral of p of x. So the minus minus, of course, makes it a plus. Integrating 1 just gives us t. So y1 is e to the t. E to the t is the solution to the homogeneous. All right, so that first step, even if it's piecewise, doesn't change what we do here. Okay, so now let's split it into the two separate pieces. So I'm going to find a U1 for the first one and a U2 for the second one. So U1 is going to be the integral of 1 over e to the t. Because remember how we find our integrating factor. We take the function that we're equal to, and we divide it by the solution to the homogeneous. So we're going to take 1 and divide it by e to the t. All right, well, that's e to the minus t. So when we integrate that, we get minus e to the minus t plus c. And I'm even going to call that c1, because that's the constant that applies to the first piece of the function. So there's my u1. Now, I also need to get a u2. I need to know what it's going to be for the second function, for the second piece of this function. But it's virtually the same thing, right? It's just now, instead of having 1 over e to the t, we have -2 over e to the t, which is going to give me 2 e to the minus t plus c2. So had there been a third piece to this, I would have found a u3. If there was a fourth piece, I would have found a u4 and so on. I just find an integrating factor for each piece. All right, well, now that I got my u's, let's get our solutions. So we're going to take y, we're going to take a y1, and we're going to multiply it to our u's. So this, I'm going to call it, this is the first part, or first piece, let's say. It's going to be y equals e to the t times minus e to the minus t plus c1. So that's going to be -1 plus c1 e to the t. That's what the first piece is going to look like. The second piece, I'll do exactly the same thing except use my other u. So I'm going to get y equals e to the t times 2e to the minus t plus c2. And so that's going to be 2 plus c2e to the t. So our solution is actually a piecewise defined function. It's going to be this thing when we're between 0 and 1. And then it's going to be this other one when we're bigger than 1. All right, so good so far? Notice that really the only difference is we had to do everything twice because there were 2 pieces to our function. Right, and this is just going to get as bad as how many pieces you have. If there are 5 pieces, you're doing everything 5 times. 20 pieces, you curse whoever gave you that and do it 20 times. Right, but it's the same process every time. All right, so we're almost done, right? The only thing we have left to do is our initial conditions. So we're going to need to use our initial condition to figure out our C's. All right, but you can probably see what the issue is now. See what the problem is, or what we're going to have to worry about here?
Yeah, one of them's not defined at 0.
Okay, so we might have to worry about being defined at 0. Really, the only thing that we have to worry about being defined at 0 is the first one, right? Because the second piece doesn't happen until we're beyond 0. But that's not the issue that I was kind of getting at. But let me lead you. How many unknowns do I have?
Just 2 no.
The less than 0 doesn't actually matter either, because we're not even turning on less than 0. But if we go to the unknowns, there are 2 unknowns, right? There's C1 and C2. Do I have enough information to get 2 unknowns?
No.
No. I've got 1 piece of information. And 1 piece of information we know is going to get us at least 1 unknown. So let's start with that. Let's start with the y of 0 equals 0. All right, so I'm gonna erase this because we've already made use of it. We've already incorporated it into our pieces. But let's look at the y of 0 equals 0. All right, so which piece does that apply to?
The first.
It's the first one, right? Because remember with our g, I probably shouldn't have raised it. The first piece was from 0 to 1, right? So when we're at 0, we're following that first piece. So let's go to the first piece and plug this in. So we're going to get 0 for our y. We're going to plug in 0 for our t. So e to the 0, of course, is 1. And this lets us solve for C1. So C1 is equal to 1. All right, cool. We got a C, which is what we expected, right? So we know that this first part is going to look like y equals e to the t minus 1. I wrote it the other way because I don't want the negative up front. Right, so it's 1 e to the t minus 1. Awesome. So we found out what the solution is to at least for the first part. When we're between 0 and 1, our function is e to the t minus 1. Okay, so good news, bad news time, right? Good news, we got one of the C's. Bad news, we still need another C. which means we need to know something else about this function. All right, ideas, thoughts? What do you think we should do here? Other than say, to hell with it and not do the problem. What do you guys think we could do?
Can we substitute in that y equals e to the t minus 1 into the second piece?
Okay, so putting it into the second piece, it's a great idea. Because I really do want to know something about the second piece, right? But I don't want to put in the first function. Because that first function turns off, right? Like you think about that y equals e to the t minus 1. That's just going to turn off when we get to 1. So what we do want, and Ralph just put, need maybe another condition. We totally do want another condition for the second piece. But I do want to circle back, because when Jesus said use the first one, we do want to use the first one. But we want to use the first one to get us an initial condition for the second. Here's what I mean. Let's think about the graph of this thing. We've got e to the t minus 1. Okay, well, we all know what e to the t looks like, right? Good old exponential growth. If we subtract 1, it just means that our asymptote's at minus 1 instead, right? So that's what this thing looks like. But we're only going to get this between 0 and 1. Right? The rest of it doesn't matter. We're only getting the e to the t between those 2 points. Because at 1, we turn on a new function. We turn on this guy. And what we need is for that second one to pick up where the first one left off. Right? Like if the idea is, I'm just trying to get one big function for the entirety, I'm going to start with this and then run with whatever the next rule is at this point. So basically, the ending point for part 1 is the starting point for part 2. So part 2's initial condition is going to be where this thing ends. So let's get this point right here. What is f of 1 going to equal? Well, if we go back to our function, it was e to the t minus 1. We know f of 1 is going to equal e to the minus 1. And this is going to be the initial condition for the second piece. So when you have a piecewise defined function, that's what we're equal to over here. This is how you need to do it. You need to use the initial condition to find the end of the first piece. The end of that first piece is now the start of the second. If there's a third piece, okay, find out where the second ends and use that to start the third. If there's a fourth one, find out where the third one ends, use that to start the fourth, and so on. So this initial condition is going to let us figure out what C2 is. So if we use that, the y of 1 equals e minus 1. We're going to get e minus 1 equals 2 plus C2 e to the 1, so C2e. if I move stuff around, I get E minus 3 is equal to C2 times E. And then dividing by E, there's my C2. Yeah. It's an ugly looking C, but it's our C2. So that means that Y, the second piece, is going to be 2 plus 1 minus 3 over E times E to the T. Now, I have no idea what that looks like, so I'm not going to even pretend to draw it here. But it's going to pick up where this one left off and do its thing. Ooh, it's actually a negative E to the T. So it's going to drop back down. Because 3 over E, that's bigger than 1, which makes that thing negative. So it's a 2 minus some multiple of E to the T. Anyway, regardless, that would give us our second piece. So here's what the solution looks like. It's piecewise. Piecewise defined, but it's going to be E to the T minus 1 when our T's were between 0 and 1. And then it's going to be 2 plus 1 minus 3 over E times E to the T once we get past T equal 1. All right. So let's just kind of take stock of this question, because I know probably right now, everything's all jumbled up in here. You're probably cursing my name. You're probably wishing we could go back to the ones we started today with. But I want you to recognize something here. What made this difficult was not the differential equation bit of it, the aspect of it, because we went through the exact same process that we did for any other one of these. We just had to do it twice, right? You had to do it 2 times, one for the first piece and then one for the second piece. But where it got complicated was the initial value problem portion. And even that wasn't so bad for the first piece. First piece, we just plugged it in, we got it. It's we had to take the end of that first piece and think of that as the start for the second. All right, so definitely more complicated. But there's a reason I showed you this. A, just to practice the differential equation. But B, because out there in the real world, you're out there and you run into differential equations. Having those that are equal to piecewise defined functions is common, very common. In fact, more common than not. Because out in the real world, where we're applying this stuff, we tend to call these forcing functions. So if I say forcing function, because I was just about to say it, having forcing functions that are piecewise defined, that's real life. Like, here's an example. You can use differential equations to model what's going on in a circuit, an electrical circuit. All right, well, suppose that we've got something plugged into the wall. Right now, there's a 0 forcing function. Nothing's going on if I haven't turned it on. I flip the switch. Now, it went from 0 to something sinusoidal because the wall is alternating current. Okay. Then I turn it off again. It drops back down to 0. That would be one that has 3 pieces. You would have your differential equation equals 0, some sort of sign, something, 0. So if we're going to be looking at, say, the current passing through the television that we've got plugged into the wall or whatever it happens to be, we would have to break it into 3 pieces. each piece would be solved the same way, but we'd have to take those initial conditions and kind of pass them along. All right, so out there in the real world, it's much more common to get a situation like this where you have piecewise defined functions in your differential equation, so your solution ends up being piecewise. All right, but the solution part is still the same. It's just the initial conditions we have to figure. All right, so you notice how I'm not asking you how you feel at this point, because I already know that I'm not going to get thumbs up, or I might, but a little sarcastically. But these are, I mean, these are tough. There are a lot of steps, but luckily they're the same steps, just more of it. All right, I think I'm going to stop here. Oh yeah, totally. We're close enough. I definitely don't want to go into the next topic. But take from today, I mean, this was a huge day, because now you know how to solve every linear first order differential equation, as long as they have solutions. Next time, we'll talk about how do you know if they've got solutions? What are the conditions you need to have solutions? Right, we'll address that next time. So yeah, I think that's good for today. So everybody have a great couple of days. I will see you all on Friday. All right, have a good one.
Thank you.